Power, say hello.
Hello.
Louder so they can hear you.
Hello.
Louder.
Hello.
Better. All right, so here's a typical orbital motion / gravitation problem. All right. First thing, we got to make sure we know what I'm asking you to find. When we say G, here's question 1. What's G at the surface? 2, what's G at position X, which is right here. So, first of all, what's G? Peep in.
G.
Louder.
Formula.
Louder. No, not formula. What does it refer to?
Gravitation.
No.
Field strength.
Yes. What? Gravitational field strength. It also refers to something else that we learned before we ever talked about gravitational fields. Sure. And specifically, gravitational acceleration. I mean, same thing, really? I mean, yes. It makes sense to refer to them differently when you're talking in different contexts, but they are the same exact thing. All right? Most of you that I've looked at your work, you know how to find it, which is great. I'm going to show you how to make sure we know how to find it, just in case you're not down for memorizing one more formula. All right, so I would take you back to situations where we first saw G in an equation. So, when and where we first saw G in an equation?
Symmetrical motion.
Sure. So free fall kind of stuff. Sure. And then when next? Yeah, forces. And in particular, we said, where do we use G in forces? Yeah, we said that an object's weight is the object's mass times gravitational acceleration. Later on, maybe we sort of figured out that it's really mass times gravitational field strength. Now, an object's weight is actually what? I know, I'm asking you to read my mind. An object's weight is actually what kind of force? No, it's not a normal force, how dare you. It's a gravitational force. And specifically a gravitational force between, let's talk about your weight right now. That's a gravitational force exerted by the Earth on you. We'll call you the object. And we know how you can express, now notice, this is a subscript, it's not a variable. That's F G. This is variable G. Now, how do we express the magnitude of a gravitational, or of the gravitational force that the Earth exerts on you? What?
Wait, what was the question?
How do we express the strength of a gravitational force? Well, those are the units we could express it in, sure. We need an equation to find the gravitational force that one object exerts on another. Yes? Yes. And what masses do we use here? Mass of the Earth, mass of you. So dig it. Whoops, massive, I should say object. So dig it. Mass of the object divides out of both sides, and we get that G anywhere is equal to G times the, well, how about we'll just say M over R squared, where M is object that makes a gravitational field, and R is what? Well, so yeah, people always say distance between the centers, but here, all we're saying is there's the Earth, or some planet. typically, or a moon or something like that. So r is the distance away from its center. From its center. So if we want to know g at the surface, what do we use for little r? The radius of the planet. If we want to know g somewhere else, like at location x, we use the distance from the center of the planet to that position. Okay, so moral of the story is you don't have to memorize, it won't kill you. You can get there in a pretty short number of steps, right? Gravitational force is mg. Gravitational force is really gmm over r squared. We can get rid of those two m's, and there's g. All right. Here's where people can go wrong and do go wrong, because this is expressed as gravitational field. People will write F for field, and then do this. Well, the field is gm over r squared. Well, that's true. The field is gm over r squared, but F refers to what? Force. So this is not true. You can't say that a force equals a field, because they're not the same thing. All right, so just make sure that you're writing the actual thing you're trying to solve for. Even though I understand field starts with F, don't write F. Write G. Happy? And furthermore, you can express G in what units? Well, for sure, based on this, we can express it in what? It's an acceleration. Meters per second squared. The field strength way, you don't typically do it in meters per second squared, but you can, because they're the same thing. All right. A couple of ways you can figure that out. You can look from here. If we just solve for G, you get F over M, right? So the units must be, it must be newtons per kilogram. That's newtons per kilogram. So when we say 9.8 meters per second squared near the surface of the Earth, we're saying, well, really we're saying the Earth's gravitational field is 9.8 newtons per kilogram. Or for every kilogram we put in the field, a force of 9.8 newtons will be exerted on it. If we were to put 2 kilograms in the field, a force of 2 times 9.8, or 19.6 newtons would be exerted on it. Okay? And we can sort of prove all this, right? Remember what a newton is? What a newton's equivalent to? A kilogram meter per second squared. So, oh yeah, if we divide both sides by yep, there it is. A newton per kilogram is a meter per second squared. Same thing. Okay? So you don't have to express one in either unit. You can express either in either unit. It's just more typical if you're asked for an acceleration to express it in meters per second squared, if you're asked for a field strength to express it in newtons per kilogram, but it doesn't matter. Okay? Fair enough? And then this orbital one, what I'm referring to here is I want the orbital velocity at altitude A of any object. All right? And so there's a couple ways to do this. And the easy way is to say, well, here at altitude A, G, which is gravitational acceleration, is really another kind of acceleration for an object moving in a nice circular orbit. It's a centripetal acceleration. And so how do we find centripetal acceleration from our circular motion days? We just do v squared over r, and you can do v is the square root of gr. Now the other way to do that is to say, well, what if I actually had a little satellite there orbiting? Well, if we did a free body diagram and said, here's its gravitational force, the centripetal force, we could say that, well, Fg is MAC and this is mass of the satellite. And FG would be G, mass of the planet, mass of the satellite, over the square of their separation, mass of the satellite, V squared over R. And the satellite goes, and an R goes with an R. And this V wait for it. This V goes G, mass of the planet over R. Well, those are the same thing. You can, if you want to, you can prove that this and this are the same thing. But I'll just trust you'll do it one of those two ways. All right? If you know G, boom, do that. And notice what this says. What does the orbital speed not have anything to do with? It has nothing to do with what object is orbiting out there. So it's a satellite. It's a piece of garbage that somebody threw out the window of the space shuttle. It doesn't matter what it is. As long as it's at this radius, it's got to orbit at that speed. Just like here, right? As long as it's at that radius, it's got to orbit at that speed. It depends only really on the mass of the thing you're orbiting and how far away from its center you are. Okay?